Hi, hello. This is part 7 of chapter 5 lecture. In this part, we are going to talk about a little bit tricky part. It's called naming polyatomic ion containing compounds. Um, it's a combination of covalent molecules that forms a ionic species. Again, it gets a little bit messier. And here's something that you need to have extra help of, looking at the chart multiple times because it's not straightforward as naming an ionic compound or covalent compound. So it gets a little bit messier. So let's discuss what is polyatomic ion is. A polyatomic ion is a combination of two or more atoms. And it gets messier because you have a covalent polyatomic ion in the form of anion that wants to combine with a cation that is a metal. So by doing that, you form a ionic species. So the complication is that you don't know what is the charge on your polyatomic ion. Phosphate is not a single element. Phosphate is a combination of phosphor and oxygen. You don't know what combination is until I showed you. In future, you would know just by getting familiarized with the names. But getting familiarized with the names is a PIA, if you know what I mean, until you get familiarized with them. Okay. Now let's discuss anyway, but with little practice or a lot of practice, you would eventually get it. Calcium phosphate. So that's the structure of the phosphate, PO4. And one more challenge is you don't know what is the charge is unless I showed you. Well, you might come across the structure in future after 2 more chapters of discussion. But for now, all you know is I need to give you the charge on phosphate ion. So phosphate ion has a charge of -3. And we already know that calcium ion has a charge of +2. So these two should form a electronically neutral ionic compound, even though it is polyatomic ion. So the ratio they exist with each other is Ca3PO4. That is how they would form neutral compound. And again, pay attention to these brackets. We are using brackets now here because you have a polyatomic ion. You don't want to mess up your coefficients of one of the elements with how many times it should be present. What it says is in this polyatomic ion containing formula, there are 3 calciums for 2 phosphate ions, and each phosphate ion contains 1 phosphor and 4 oxygens. Okay. Here are some of them for common polyatomic ions. Again, once you know it, and sometimes you need to refer to table a lot. There are some of them easy to identify, and some of them are hard to identify. These two are always my favorite, and they are going to be your favorite in a couple terms, like in last term of this year, hydronium and ammonium ions. And maybe cyanide is easy to identify. Just know that we are going to use these two a lot. So maybe you just get used to them. And others are hydroxide is something that we use a lot in future. And let's see, anything that I see very commonly we use. Not so much, not so much. Maybe sulfate I can say, but not so much. Not all of them are very common. So you only need to know for the sake of naming, at least for now. Maybe in future, I might need you to do more things with it. You just need to use some help or maybe flashcards until you get familiarized with these topics. Let's see what is going on here. So the problem is asking us to name the following ionic compounds. What compounds they were is FET, Fe2SO4 3. So it is asking you to name that compound. Let's see what is the strategy. Your strategy is going to be, well, it just asking you to name, but whenever you have a metal that is not from group 1, 2, and 3, you need to know that you need to include the charge in the form of a Roman number next to the name of it. We know that that is iron, Fe is iron, and you need to know what is the charge on the sulfur SO4. SO4 has a charge of -2. How do I know? I know it by familiarizing with SO4 over the years. So that's what you have to do. So SO4 has a charge of -2. So -2 times 3 SO4s. And you're looking for overall charge of 0. You have 2 iron, and what should go there? There should be +3. That's the charge of your iron. So your name of the iron should be iron 3 sulfate. That is how you would name it. How do you name AlOH3? So you need to know that aluminum is from group 3. So group 3 element will have a fixed charge of +3. And now you need to have the overall neutral charge. And it said there are 3 OHs. And to have a overall neutral charge, you should have negative charge 1. So now you need to know the name of this OH. OH is called as hydroxide. It's a polyatomic ion. It has a fixed name. So the name is aluminum hydroxide. And what is the name of Hg2O? Hg is mercury. Mercury is not from group 1, 2, 3, which means you need to include its charge in Roman number. How do we identify? We can rely on oxygen with its -2 charge. So oxygen -2 charge, there is 1 oxygen. You are aiming for overall neutral charge. There are 2 mercuries. How do you get overall neutral is if mercury has +1 charge. So name is going to be mercury 1 oxide. That is how you would name it. Okay, I'm not saying it's easy, but with practice, you can do it. Let's look into some more complicated polyatomic ions. One of the polyatomic ions that usually confuses people is oxyanions or oxoanions. Oxoanions we discussed 4 of them, and those names look really close. So good luck in separating one from another, but I'll do my best to help you how to differentiate one from another. First, I want you to look at the most common oxoanion, which is chlorate. Chlorate contains 3 oxygens for 1 chlorine, okay? And depending on how many oxygens are connected to per single chlorine, your name of the oxoanion is going to change from 8 to different, okay? Let's say if you have ClO4 instead of ClO3, your name will change to perchlorate ion. Everything same, but you add the word per in front of it. Let's say you only have 2 oxygens for 1 single chloride. In this case, your name changes to chloride. Now it is called a chloride. Let's say you only have 1 oxygen for 1 chlorine. In this case, name changes to hypochlorite. Hypochlorite. Again, these are the things that you need to get familiarized with. Here, what we have is the different types of oxoanions. Perchlorate, chlorate, chloride, hypochlorite, and there are 2 different kinds of nitrogen-based oxoanion, 2 different kinds of phosphorus-based oxoanions, 2 different kinds of sulfur-based oxoanions. So kind of you need to refer to this until you remember well. People don't really harass you, asking you to name these compounds, even including me. Kind of, kind of try to help you instead of trying to harass you and trying to remember these names at this in general chemistry. And if you happen to take more chemistry, if you're a chemistry student, you don't really struggle with them in future after a few years. Even now, I kind of have to double check just to make sure if I'm saying right or wrong before I say it. It's very common for most people to refer to this chart before we say the name. If you have to do it, just do it. It's very common. You don't have to, Ashamed about it because I'm not. All right. Other types of oxygen-based compounds are called oxoacids, and these are similar to what we just looked at, oxoanions. In oxoanions, you don't have hydrogens, but oxoacids has hydrogens. That's the only difference. So ClO3 is a chloride, right? But if you have hydrogen for that ClO3 minus, to make it a neutral molecule, it changes to chloric acid. So usually ends changes. And if you have hydrogen connected to HClO2, it's converted to HClO2. So name change it to chlorous acid. It change it to us acid. And these are the things we kind of have to remember. And whenever you have other ratios like HClO4 and HClO, the name change it to perchloric acid instead of perchlorate, and hypochlorite change it to hypochlorous. So some similarity, we should say, at least. Other less popular oxoacids are, we can call them as monoprotic or polyprotic. These are, common names, kind of have to remember with those names, like, phosphoric acid and dihydrogen phosphoric acid and hydrogen phosphate ion and a phosphate ion. They just kind of indicate how many hydrogens there are present, because from here to here, you have one hydrogen less, here to here, you have one hydrogen less, here to here, you have one hydrogen less. It's kind of, keeps you track of how many hydrogens left, because this is the parent molecule, phosphoric acid, and from that, you derive rest of the two names as dihydrogen phosphate ion or just monohydrogen phosphate ion or phosphate ion. Okay. Let's see, it is asking us to name these compounds, and let's try to name these compounds. Name the following species. BrO4. What is the BrO4 is going to be named as? BrO4 is containing one more oxygen than BrO3. So instead of saying a bromate ion, we are going to say perbromate ion. And HCO3 contains a hydrogen connected to CO3 ion. And we know that CO3 is called a carbonate ion. So we call HCO3 as hydrogen carbonate ion. And H2CO3 contains two hydrogens connected to carbonate ion, so it combines with a specific name called carbonic acid. It's kind of like, special name, carbonic acid. We kind of have to, remember that name like that. These are some of the most popular oxate ions like ClO3, IO3, BrO3, sulfate or phosphate, nitrate, carbonate, oxalate, chromate, and permanganate. We kind of have to remember those because these are popular. These are most popular ones. Let's see, it is asking, let's see, the question is asking us to determine the formula of sulfurous acid. Sulfurous is erased because, remember, whenever you have the name ends with us, it is generated from something that contains only two, or not two, I want to say two oxygens, but in this case, let's see. If you have, well, I want to use the carbonate and oxygen name, so that's where I make the wrong. SO4 is sulfate and SO3 is a sulfite. So SO3 2 minus is sulfite, but when SO3 2 minus connected to hydrogens, it is called sulfurous acid. That is how you would derive the name. Sulfurous acid chemical formula is H2SO3. Few more names, and here I guess maybe this is one of the easier way to name a compound. Hydrates are compounds ionic compounds, but some ionic compounds have a nature of attracting hydrogen molecules, like water molecules, towards them. So in those cases, we name those molecules as hydrates. We name the actual ionic molecule as its own, and we just say how many hydrogen molecules that are present are connected to it. For example, CuSO4 is named as copper 2 sulfate, but it has the ability to attract 5 water molecules. So once you name copper SO4 as copper 2 sulfate, you need to tell how many hydrogen molecules it is attracting by saying pentahydrate. So name is copper 2 sulfate pentahydrate. Similarly, there are some other molecules that have similar nature: barium chloride dihydrate, lithium chloride monohydrate, magnesium sulfate heptahydrate, strontium nitrate tetrahydrate. That's how you would name the molecules. These hydrates, again, they were not part of actual frame of the ionic compounds. They were just attracted to that ionic compound. So sometimes, water, if you just heat it, it would evaporate. It is one of the examples what happens if you dehydrate the hydrate molecules. Copper sulfate pentahydrate is actually blue in color structure if you look at it at room temperature, but if you heat it at 100 degrees Celsius for a few minutes, it would change to white color. What it means is you are able to remove the hydrogens, water molecules from it, because it's not part of the structure. That's why we use this dot. This dot means it's not the actual framework of the ionic compound. They were just, hanging onto it, kind of hanging around. These are some of the common familiar inorganic names. Like we said, water is popular instead of saying hydrogen monoxide. Like ammonia is popular by its name. Dry ice is popular rather than saying solid carbon dioxide. Salt is popular than saying sodium chloride. And like nitrous oxide or marble, that's carbon CaCO3, or baking soda, instead of saying sodium hydrogen carbonate, really long name. Epsom salt is popular than saying magnesium sulfate heptahydrate, and milk of magnesia is popular than saying magnesium hydroxide. These are just common popular names. Again, this section, as you see, polyatomic ions can be a little bit tricky, and especially naming oxoanions and oxoacids can be challenging. But it gets, I wouldn't say easier, but you get used to it eventually, because there are not so many of them. There are enough of them that gives you challenge, but eventually you get familiarized with them. Again, I'm not going to stress you a lot on this. I want you to be able to name some of the easy ones, not really complicated ones. I'll see you in another part of this chapter lecture. This is all for this part.